My name is Seung Han. Today I am happy to present our recent work on MyTEE on the trusted execution environment on embedded device. This is a joint work with Professor James Zhang. We are from Chungnam National University. Today, the trusted execution environment is widely adopted to isolate and protect the trusted application and private data. TrustZone is a security feature to build the TEE on ARM architectural device. With the TrustZone, CPU states are divided into non-secure and secure state. In each state, user, kernel, and hypervisor modes are supported. In addition, the monitor mode plays a role as a gatekeeper between the non-secure and secure state. It generally saves and restores the kernel context. It generally saves and restores the context of each environment. In addition to the CPU state separation, TrustZone enables to protect the memory and peripheral. This is achieved by providing TrustZone hardware extensions. For instance, TGAESC enables to enforce a certain memory to be accessed only when CPU state is insecure. The TGPC dynamically configures a peripheral to be either insecure or non-secure state. By leveraging such CPU state and hardware extensions, device manufacturer compose a TEE. In addition to the TrustZone, ARM architecture also supports hardware-assisted virtualization technology. The virtualization technique provides the stage 2 paging, which introduces additional address trace layer that convert the intermediate physical address to the real physical address. Hence, by crafting the staged page table, we can isolate VMs from each other. Page fault due to violating the access permission settings in the stage 2 page table is delivered to the hypervisor. This feature has been prevalently adopted by industry and academia to build various security applications such as kernel integrity monitor and application shielding. As an example application of the TEE, the real-time kernel protection RKP technology leverages the TEE to isolate itself from the untrusted OS. It deprivileges the OS and enforces the security critical operation to be performed in the TEE to protect the OS kernel integrity. For instance, when every context switch happens, the OS requests the TEE to update the page table-based register. In the TEE, such operations are verified and evaluated. Although the TrustZone defines the security feature for building the TEE, real-world implementation of the TrustZone extension in SoC is optional. Therefore, some SoCs do not support the extension, so they cannot build the security. The SoCs that lack the extensions are hosted in low-end mobile phone and tablet PCs to reduce production cost. To resolve this problem, we provide an alternative solution for creating TEEs without depending on hardware trust extension. To achieve our goal, we propose two key techniques to enable the TEE memory isolation and the secure I/O without depending on TrustZone hardware extensions. They are designed based on assumption that the integrity of the firmware and OS is properly protected by RKP and secure boot. Also, we do not assume the physical and side channel attacks. This figure describes the component of MyTEE, a framework for achieving memory protection and secure I/O. This highlighted component aims to protect the memory without depending on TrustZone extension, the TGAESC. First, we leverage the staged paging to isolate the TEE and hypervisor from the untrusted OS. This is simply performed by removing the mapping to the TEE and hypervisor in stage 2 page tables. In addition, we isolate stage 2 page table in the TEE to protect them even with the compromised hypervisor. Second, we deprivilege the kernel to verify and evaluate every security critical operations of OS, such as page table update. Whenever the critical operation needs to be conducted, the OS has to request them to the active integrity monitor. We have adapted the RKP to achieve this. The attacker can maliciously program the DMA controller to bypass the paging-based memory protection. To defeat this attack, we implemented DMA filter running the hypervisor mode. DMA filter first write to protect the DMA ML region to monitor any write attempt of control block that defines the DMA information such as source and target and size of data. Any write to protect the region generates the stage 2 paging fault. Once the fault is trapped by hypervisor, the linked control blocks are copied into secure memory. Then each control block is checked if it programs the DMA controller to access protected regions and objects. After the verification, MyTEE writes the copied control block address to the control register. Because control blocks are flashed in the protected region during the DMA transaction, we can prevent the time check to time user attack. From now on, I'll explain how the secure I/O is established by MyTEE. First, the ML region and DMA buffers are write protected by stage 2 paging. Thus, OS and device driver cannot access them. Then, we temporarily escalate the privilege board of code blocks in the device drivers so they can access shared object. Because we leverage the existing device driver instead of hosting the device driver in the TEE, we can prevent blotting the TEE. The temporal privilege escalation technique exploits the fact that kernel mode execution is affected by both the shared page table and the stage 2 page tables. But hypervisor mode execution is not affected by the stage 2 page table. As shown in this example, the secure buffer and MMIO region are imposed to be not accessible in the kernel mode because the stage settings in the stage 2 page table is more restrictive than that of the shared page table. However, the buffer and MMIO region are accessible in the hypervisor mode because the stage 2 page table is not used in the hypervisor address translation. By using the MyTEE API framework, we escalate the privilege of code blocks to the hypervisor mode that then need access to protect object. We can also return back to the kernel privilege by using another API, MyTEE preview. This example code performs the MMIO with mailbox. To secure I/O, we can instrument the device driver by using another MyTEE APIs. Let's assume that the MML region for the writer is already write protected. We wrap the writer function with some verification APIs and escalate the privilege of the wrapper function. For details, please refer to our paper. For the temporal privilege escalation, the shared and the stage 2 page table are used. To protect the stage 2 page table, we place them in the region that is not mapped by both the shared page table and the stage 2 page table. The shared page table are set to read-only, so only the active integrity monitor can update it. Because the hypervisor also uses the same page table for each one address translation, the read-only permission is enforced during the hypervisor mode execution as well. From now on, I'll show you the example secure I/O application that communicates with the hardware TPM chip. compared to the normal TEE usage scenario, peripheral device driver, control device driver, and hypervisor are involved in the MyTEE supported secure I/O. In our example scenario, the TA communicates with the hardware TPM chip. First, the TA creates the TPM command and stores it in the secure memory allocated hypervisor region. The TA notifies the CA that the payload is prepared and a new transaction can be started. The CA invokes the TPM device driver to start the transaction. The MyTEE Shield MMR API is invoked to protect the TPM MMR region. Because it requires to update the stage 2 page table, the request is sent to the active integrity monitor. The integrity monitor updates the stage 2 page table to remove the mapping to the TPM MMR region from the OS. Thus, the untrusted OS cannot read or write the TPM. In addition, the integrity monitor updates the secure log with the shielding operation. After that, it returns back to the TPM device driver. The driver prepares the SPI protocol message for the TPM. The message is sent to the SPI control driver to trigger the communication with the TPM hardware. As the MMR region for the TPM is protected, the control driver cannot access it. Hence, we escalate the publication of code blocks for MMIO using the MyTEE API. The API simply invokes the hypercore, so the CPU mode switches to the hypervisor. After some security configuration, it returns back to the device driver without deprivileging to the kernel mode. Now, the driver code runs in the hypervisor mode, so it can perform the MMIO. Besides, it loads the command written to the TPM for future validation by the trusted application. The TPM performs the requested operations such as random number generation, and the result is read and written to the secure I/O buffer by the privileged code blocks. Once all the previous operations are conducted, it invokes MyTEE PrivDown API to lower current privilege. The hypervisor restores the kernel context, switches the CPU mode to kernel, and returns back to the controller driver. Once the transaction with the TPM is completed, the CA gets the control back. It notifies the transaction completion to the TA. The TA maps the secure log and I/O buffers, verifies the log, and consumes the result from the TPM. Several attack surfaces to MyTEE and TPM measure can be summarized as follows. First, to defeat the malicious command injection to the peripheral that is involved in the secure I/O, will log and verify every command to the peripheral device. To prevent API abusing, we will restrict the API to be invoked only from the statically compiled context. To secure DMA, we verify and emulate any MMIO that aims to configure the DMA controller. Finally, the privileged escalate or memory operations can be abused to corrupt the protected region. To prevent this, we verify the source, target, and size of memory operation in the privileged escalate code block. Let me skip the performance evaluation due to the time constraint. In conclusion, we propose MyTEE that enables to build the TEE without depending on TrustZone hardware extension. In addition, to show the feasibility of our approach, we implemented POC on Raspberry Pi 3 and demonstrates secure I/O application. Thanks for listening. I'm happy to take any question.
Yoshi from UC Irvine. I was just curious about if you have any thoughts on supporting remote attestation on MyTEE. I know this is a bit of a, not a great question because I know TrustZone does not support remote attestation by default, but do you have any ideas how to support remote attestation on your system?
Sorry, how to
Remote attestation. So when you deploy, for example, an application inside your TEE, you want to check whether that code that is running inside the TEE is expected code. And like SGX has remote attestation, other TEs also have attestation to what I wanted to hear your thoughts about supporting that.
Uh, I'm sorry. I still don't understand your question. Could I come back to you earlier?
Okay, yeah, sure.
I'm sorry.
Yeah, I guess maybe you guys can talk more offline, I believe. Yeah.